In a previous video, linked below, it was shown that Nicholas Carnot was the person who derived the second law of thermodynamics through the Carnot cycle. Carnot was trying to theoretically determine how efficient a steam engine could be because this was the Industrial Revolution. So he had an engine composed of a perfect gas expanding against a frictionless cylinder from a high temperature reservoir adiabatically to a low temperature reservoir isothermally, and then back up to the top. The net result was his statement of the first law of thermodynamics, which was the efficiency of the engine is basically related to 1 minus the temperature of the low temperature reservoir over the high temperature reservoir. So the efficiency had to be less than 1, and no perpetual motion was possible. You can't make an engine that's 100% efficient. Additionally, since heat is proportional to temperature, at any given point, the heat transfer divided by the temperature is equal to a constant, the heat capacity. You had a new state function developed. Starting from the beginning, going to the back, to the end, Q high over T high minus Q low over T low is going to be equal to 0 because you're starting and ending at the same point A. This is a state function by definition, and the state function was called entropy, defined permanently as delta S is equal to the integral of the change in heat over the temperature. How is entropy actually used? A tenet of thermodynamics is that a thermodynamic function can only be solved for a reversible process, a process conducted in an infinite number of infinitely small steps. In reality, this is not possible. Everything is done irreversibly. Water can roll down the hill, it can't roll back up on its own. On the one hand, an irreversible process seemingly cannot be solved for thermodynamically, which means it can't be predicted. But on the other hand, it is the only possibility that occurs. As mentioned, the reversible process was developed purely for the sake of thermodynamics as a theoretical construct, but it does not happen in real life. The second law connects the two of them by creating what's called a reversible pathway. It says essentially that you can take any irreversible process and convert it into a reversible process to determine the thermodynamic properties of that process. If I look at the change in entropy for this pathway, thermodynamics is always final minus initial, where my final state is dq reversible over T minus my initial state dq irreversible over T. The whole point of reversibility is that it is the most efficient, the maximum amount of heat or work you can get out of a system. Therefore, it's the only one that can be determined. So in any given situation, reversible heat or work will always be greater than irreversible heat or work. So delta S for this reversible pathway has to be greater than 0. This leads to a perhaps more familiar statement: a process occurring spontaneously in an isolated system must be accompanied by an increase in entropy. Or, since the universe is the definition of a spontaneous isolated system, the most common statement: the entropy of the universe is increasing. These two statements are the more familiar statements of the second law of thermodynamics, but they arise from the actual statement that you cannot create a 100% efficient engine. Now, how do we use it? Seemingly trivial statement: if reversible minus irreversible is positive, irreversible minus reversible is negative. Since entropy is defined as the integral of dq over T, you can call dq reversible T times the change in entropy. You'll notice here in the universe you have your four variables: temperature, heat, volume, and pressure. The definition of entropy already has temperature and heat in it. That leaves you with two variables left. If I do a process reversibly by holding the volume constant, the following is true. dq at a constant volume minus dq reversible is going to be less than 0. The definition of dq at a constant volume is the internal energy. dq reversible is T delta S. This gives you a new function called the Helmholtz energy, defined as delta A is equal to delta U, the internal energy, minus delta TS. Expanding this out, the internal energy is heat minus work, dq minus pdv. The total differential of delta TS is TdS plus SdT. So I get delta A is equal to the integral of TdS minus pdv, delta U, minus TdS plus SdT, delta TS. The TdS's cancel out, and I get what's called a fundamental equation. Delta A is equal to the integral of SdT minus the integral of pdv. This is called a fundamental equation because it is given purely in state functions, where A is a function of temperature and volume, and the change in both of those. I move on and do something in a constant pressure. Now my system is going to be dq at a constant pressure minus dq reversible has to be less than 0. dq at a constant pressure is the definition of enthalpy, H. This is the Gibbs free energy, defined as something that you might find familiar from general chemistry. Delta G is delta H minus delta TS. I expand this out, where delta H is delta U plus delta PV. Delta U is dq minus pdv. The full integral of delta PV is pdv plus vdp. And I get a very, very long statement where delta U ends up TdS minus pdv. I get a lot of things. I get the TdS's canceling out, the PdV's canceling out, and the fundamental statement for the Gibbs free energy is minus the integral of entropy times the change in temperature, plus the integral of volume times the change in pressure. These two new thermodynamic functions have one thing in common. First of all, since the irreversible minus reversible pathway has to be less than 0, in both cases, delta G or delta A indicates that a negative answer will be a spontaneous process. Secondly, they look similar but yet not identical. In the Helmholtz energy, the Helmholtz energy relies on minus pdv, which is the definition of work. Engineers use Helmholtz energy because it gives you the maximum mechanical work a system can do. The Gibbs energy, on the other hand, is related to the opposite of work, VDP, which is the maximum non-mechanical work a system can do. Examples of non-mechanical work would be chemical work, electrical work, or nuclear work, which is why chemists are more familiar with delta G. In terms of the thermodynamics of the systems, you now have a complete set of definitions of all of the possible thermodynamic functions. You have, by definition, thermodynamics is heat, dq, plus work, dW, which is thermodynamically defined as minus the integral of pdv. The internal energy is heat plus work, which is equal to the heat capacity at a constant volume dt. Your other variable not used so far, the enthalpy is equal to the heat capacity at a constant pressure times dt, or delta U minus work. The second law gives you the definition of entropy, the integral of heat change over temperature. Helmholtz energy, minus STT minus PDV. And Gibbs energy, minus STT plus VDP. These are all the answers in thermodynamics. These are the definitions of all of the thermodynamic functions. So it then becomes a matter of how do you apply them. To apply a thermodynamic function, you have to have a reversible process, and to have a reversible process, you have to keep one variable constant. So we start with an isothermal process with a change in temperature of 0. You look for the functions that depend upon temperature, and you see those are the internal energy and the enthalpy, so they will still be 0. If the temperature is constant, pressure cannot be constant, so you have to substitute. So work minus PDV, substituting pressure for RT over V, you get work is minus RT log V2 over V1. Since the internal energy is 0, the heat is going to be opposite to whatever the work would be, or plus RT log V2 over V1. The definition of entropy does not change. It's dq over T. So if you calculate dq first, isothermally occurring at one temperature, divide that value by the temperature, you get delta S. Since the change in temperature is 0, minus SDT is 0, so delta A is simply equal to work. G is equal to VDP, but again, since temperature is constant, plus RT log P2 over P1 is minus RT log V2 over V1, as was shown in the previous video, so delta G is also work. If I move on to another variable and keep heat constant for an adiabatic system, you see obviously heat is going to be 0, and the other thermodynamic function that depends on heat is entropy, which will also be 0. Delta U is always CV dt. Delta H is always Cp dt. Since work is equal to delta U, you can find two temperatures and two volumes, and also find delta U, as was shown previously in a previous video. Since entropy is now 0, minus SDT is still 0, so delta A and delta G still equal work. Okay, since A and G are functions of Q and T, or P and V rather, they're essentially independent of heat and temperature, so you will always get the same answer. I move on to a constant volume. Work is now 0. Delta U is always CV dt, which will also be the heat flow for the system. Delta H is always Cp dt, and with the volume staying constant, temperature can change. Entropy now is now heat at a constant volume, or Cv dt over T. So the entropy becomes Cv log T2 over T1. At a constant volume, PDV is 0. So the Helmholtz energy is the change in entropy, which is already found, times dt. Gibbs energy is the one that you actually have to put some work into this time, because it's not going to be connected to any of the others. You have minus SDT, and you have to calculate the value of VDP based on the conditions given. Finally, at a constant pressure, Delta H is defined as Cp dt, which is also the heat at a constant pressure. Internal energy is Cv dt, is also heat plus work. So work is delta U minus the heat, or delta U minus delta H. Similar to the previous, entropy is always heat over temperature. Heat in this case is Cp dt, so you get Cp log T2 over T1. In delta G, with a constant P, is now simply equal to minus that value of entropy times the change in temperature. And delta A is minus entropy times the change in temperature plus work. So there are many different possibilities based on the 4 different conditions that could be held constant. They're all related to the fact that your fundamental thermodynamic definitions never change. So in each case, you simply look at which condition is being held constant and find out how that impacts your working definitions. A video will show up later where we will go through these with worked examples. Now, that is everywhere you could solve a thermodynamic process for a theoretical reversible system. What happens in the real world? What happens if I have a 10-gram ice cube at minus 10 degrees C and I melt it at 25 degrees C? What is the change in entropy? This is the definition of irreversible, because at 0 degrees C, water freezes or ice melts, you have an equilibrium. At 25 degrees C, ice melts. It will not refreeze. That is irreversible. So one develops what is called an irreversible process, or an irreversible pathway. I break it down. I have water at minus 10 degrees as ice, and I bring that up to 0 degrees reversibly at a constant pressure. At 0 degrees at a constant temperature, I turn the solid water into liquid water, and then I take the liquid water and, again at a constant pressure, increase the temperature to 25 degrees C. The total entropy is going to be the entropy of step 1 plus step 2 plus step 3, or will follow Hess's law. So in the first case, entropy is always the integral of dq over t. At a constant pressure, that is equal to c dt over t, or the heat capacity at a constant pressure, log T2 over T1. In this case, I'm using a real substance. So I have the heat at a constant pressure is going to be 10 grams of ice times the specific heat of ice, 2.9 joules per gram degree Celsius, log of where I end, 273 K, over where I begin, 263. I get a change of entropy of 1.08 joules per degree Kelvin. For the second step, entropy is still the integral of dq over t. In this case, the ice is melting. The dq is simply the heat of fusion, which for ice is 6,020 joules per mole. I have 10 grams divided by 18 grams per mole, and ice melts at 273, gives me 12.25 joules per degree Kelvin. Third step, dq over t is c dt over t, log, or the heat capacity, log T2 over T1. The specific heat of water is 4.18 joules. The specific heat of liquid water is 4.18 joules per gram degree Celsius. I have 10 grams. I'm ending at 25 degrees C, or 298 K. So I get 3.66 joules per degree Celsius. So for the entire process, or to melt an ice cube at 25 degrees C that was initially made at minus 10, the change in entropy would be approximately 17 joules per degree Kelvin, or 16.996. Entropy also plays a role in explaining another phenomenon that is apparent in the world, mixing. I start off theoretically with two perfect gases, A and B. 2 steps. Firstly, I expand each gas reversibly and isothermally so that the final volume is going to be equal to the total volume of both initially. So the final volume is VA plus VB. Since this is done isothermally, the internal energy and the enthalpy changes are 0. The entropy would be the entropy of gas A plus the gas B, or N R log V final over V. So N of A R log V final over V of A plus N of B R log V final over V of B. I then mix the gases through a membrane reversibly and adiabatically. Since it's adiabatic, dq is 0. Since the change in volume is also 0, work is 0, so enthalpy and internal energy are 0 for the second step. Entropy is also 0 for the second step. So for the entire process, internal energy and enthalpy are 0. Essentially, two substances will mix together even at a constant temperature. There is no energy term to mixing two things. However, the entropy of mixing is going to be equal to the first step, already shown, moles of A R log V final over V of A, moles of B R log V final V of B. Since the final volume is the volume of A plus B, V final over any given component is going to be 1 over the mole fraction of that component. The log of 1 over x is equal to minus the log of x. So I get a useful statement on the entropy of mixing that it's going to be equal to minus the total number of moles present times the sum of the mole fraction of each component times the log of the mole fraction. Besides being useful academically, this is also a very profound statement where you have the knowledge that entropy is also described as disorder, and disorder is favored in the universe. This is essentially the proof of it. There is no energetic reason why two materials will mix together, even if they're put in contact. Thermally, if they're at equilibrium, they should just sit still. There is no impetus for them to move. There's no energy provided. Yet they will always mix. That's because of entropy and the entropy of mixing. Mixing creates disorder. So if the entropy of the universe must increase, that means the disorder of the universe must also increase. I hope you found this video useful. A following video will describe how to use these derived equations in actual problems, and also a useful set of things called Maxwell's relations, which show how all of the thermodynamic properties are related to each other. Once again, thank you for watching, and I hope